Consolidation is one of the most important phenomena in geotechnical engineering. Whenever a soil is loaded, one can expect settlement. Consolidation is a two-phase process. The first phase, also known as primary consolidation, involves the expulsion of voids. The second phase is the actual rearrangement of intergranular particles, and this is known as secondary consolidation. Fine-grained soils are the most prone to settlement or consolidation issues because of the number of voids available for expulsion. Fine-grained particles have larger surface areas than coarse-grained particles, thus more voids. Primary consolidation is a serious and dangerous issue that must be addressed when building over silt or clay layers. This is a picture of an apparatus used for consolidation testing. The soil sample sits between two porous stones and is compressed vertically, similar to a footing or roadway load. The test emulates field conditions and is a means of predicting not only settlement, but settlement with time. The tools used for the test are shown here. Loading discs or weights to produce axial stresses. The loads will proceed in an increasing manner, they are just not shown here. Next, wire saw, cutting knife, and straight edge for sample cutting. Consolidation rings with beveled edges. The ball and top platen, setting cup with a porous stone at the base. The sample fits within the ring's inner volume and sits on top of the porous stone, then porous stone above, and finally top platen and ball. Load is applied to the ball so that a uniform load is distributed across the area. Here's a wrench for the hydraulic jack, and we need a hydraulic jack for removing the sample. Not shown is the consolidometer, which will later be used. Jack the sample out of the Shelby tube until its full length is exposed. Carefully remove the specimen from the plate. Place the undisturbed sample flat on a table. Do not forget to weigh the cutting ring that will be used during the test. Place the cutting ring flush onto the top of the specimen and slowly push the ring down. Push the ring down to desired testing depth. Use the knife to trim around the outer perimeter of the ring. Saw or cut the ring from the rest of the sample. For soft specimens, use the wire saw to flush the sample with the flat surface of the ring. The wire saw reduces smears on soft soils. The wire saw is used here because the sample is considered a soft clay. Saw or trim the specimen until the sides are flush with the ends of the ring. Clean off the entire outside of the ring and beveled edges. Take 4 independent thickness measurements of the sample and average the 4. Weigh and record the mass of the wet soil and ring pre-test. Also weigh a tear and place a portion of the leftover undisturbed soil in the tear for a moisture content determination. Place the tear in the oven to dry at 110 degrees Celsius. The incremental loading schedule. We will apply these axial stresses onto the sample according to this regimen. The vertical deflections will be measured throughout the duration of the load. The incremental loading schedule must be predetermined so that the calibration can be performed along the same regimen. The loading schedule should be determined based on the project's construction schedule. If a building is to be built vertically, floor by floor, then this schedule makes sense. On the other hand, if fill is to be added, then later removed to address consolidation concerns, then an intermediate rebound or unloading should be added within the schedule. The plot shown here is similar to the one we will produce for our test specimen. Void ratio as a function of log of axial stress or log pressure. We must first define the term void ratio. The void ratio is the volume of the voids relative to the volume of solid particles. Each point on the plot represents the end of a loading increment, and the previous load's corresponding void ratio for the sample. The higher the axial stress on the sample, the lower the void ratio. Calibration for the consolidation test involves finding deflections of the porous stones and filter paper caused by the load. First, we soak the filter papers and porous stones in water for approximately 2 minutes. We strive to run the calibration just as we will the actual test. After 2 minutes, remove the porous stones and filter papers. We utilize a steel disc similar in dimension to the test sample, which will display no deflection during calibration. Place filter papers on either side of the steel disc and porous stones on either side of filter papers. Place the top platen and ball on top of the porous stone once the calibration disc is in the cup. Swing the load beam over and seat it on the ball. Tighten the wing nuts on both ends and ensure everything is flush with the calibration disc. Position the LVDT so that its tip rests on the load beam. The first axial stress that we will apply to our sample is the 1/8 of a ton per square foot. Select the calibrated weight disc that corresponds to this load. Tear or zero out the vertical LVDT. Then place the weighted disc on the carriage. Allow for settlements to occur. Allow enough time for all settlements to develop. Once consolidation has fully occurred under that pressure, record the deflection. Replace the next axial stress on the load scheme with the current. In our case, we replace the 1/8 of a ton per square foot disc with the 1/4 of a ton per square foot disc. Again, wait for full consolidation and record the value. Repeat this process in the same order as in the predetermined load schedule. The end result should be all of the axial stresses with an associated machine deflection. The machine deflection was 0.0177 inches under the 16 ton per square foot stress. These deflections will later be applied so that they are not incorporated into the actual sample deflection. The test. The first step is to set up the time displacement interval table. For best results, obtain the same number of measurements per log cycle. For instance, 10 readings per log cycle would give you 10 readings within the first 6 seconds of the test, or 1/10 of a minute. 10 readings from 6 seconds to 1 minute, and so on. This table is an example of obtaining 10 readings per log base 10 cycle. Next, select the load sequence unique to your project. Enter the machine deflection into the associated load table, if applicable. Some softwares automatically take machine deflection into account. Next, place the trim sample into the cup on top of the porous stone. Be sure the beveled edge is pointing in the upward direction. Place the filter paper, then porous stone on top. Place the top platen and ball on top of the porous stone. Make sure everything is flush and will bear down evenly on the sample. Swing the load beam over and seat it on the ball. Tighten the wing nuts on both ends. Position the LVDT so its tip rests on the load beam. Set the start condition so that the readings will begin right when the first load is placed on the carriage. Place the first load on the carriage at the same time the clock starts. Add enough water to the cup to fill the sample completely. Dial readings will be recorded at this time. Once the secondary consolidation phase is complete, the next load increment is ready. We will later explain secondary consolidation in detail. Stop recording dial readings. Record the first and final dial readings. Place the next load on the carriage while simultaneously starting the clock. Repeat the process for the remaining axial stresses in the sequence. For the stresses above the pre-consolidation pressure, normally 1 TSF, plot dial reading as a function of log time. Also plot dial reading as a function of square root of time. These plots are helpful in determining important consolidation parameters. Once the test is finished, remove the sample and ring from the cup. Dry the surface of the sample and weigh the sample and the ring. Dry the sample in the oven at 110 degrees Celsius overnight. Time deformation plots are graphs of dial reading as a function of time. The deformation plots will lead us to an important parameter known as the coefficient of consolidation. The coefficient of consolidation is a parameter that relates time and consolidation or settlement. So when this value is found, settlements with time can be predicted. To find the coefficient of consolidation, we utilize the listed equation. CV is equal to T time factor times drainage path of clay layer at 50% consolidation, all squared, divided by the corresponding time T. There are two established methods for finding T50 and D50. Casagrande's method, which utilizes log time, and Taylor's method, which utilizes square root of time. We must use these methods to solve the shown equation. First, we will overview Casagrande's method. The first assumption is that the construction for D0, deformation at 0% consolidation, is based on the approximation that deformation versus time is parabolic for degrees of consolidation less than 60%. The reason for this is because D0, the deformation corresponding to T0, 0 time, is not displayed on a log scale. We must use the parabolic assumption to extrapolate where D0 would be if the log scale did display 0 time. Another assumption that Casagrande's method makes is that the construction for D100 is empirical. Finally, D50 is calculated based on an average. D50 is equal to D0 plus D100, all divided by 2. The time corresponding to D50 is T50. Let's look at a construction as an example. This is a typical dial reading as a function of time plot on a semi-log scale in red. Each load increment will have a unique point, such as this. The various points in red are displacement measurements with a corresponding time from the start of the test. First, we need to find D0, the corresponding deformation at time 0. Since there is no 0 on a log scale, we assume the same parabolic distribution that we already see within the early portion of loading. To do this, we select T1 to be a time within the initial parabolic portion and less than 60% consolidation. For convenience, we take T1 to be 1 minute. T2 is 4 times T1, therefore in our case T2 is 4 minutes. Find the corresponding deformation D1 and D2 as shown. D1 is equal to 950, corresponds to T1 equal to 1 minute. D2 equals 985, corresponding to T2 equal to 4 minutes. The vertical distance between D1 and D2 is known as delta. In this case, D2 minus D1 is 985 minus 950 equal to 35 vertical units, which is delta. The trick is to move up a vertical distance delta from D1. By reflecting a horizontal line a distance delta from D1, we obtain D0 equal to 915. This is the initial deformation if time 0 were to exist on a log scale based on the parabolic assumption. Our next task is to find D100. D100 is empirical as mentioned previously. Thus, it is the corresponding dial reading at the intersection of the tangent lines from the primary portion of the curve and secondary portion of the curve. So draw a tangent line from the primary portion of the curve that fits the straight line portion of the primary consolidation data. Then draw a straight line tangent to the secondary consolidation data points. Extend both lines so that an intersection is made. The corresponding dial reading at the intersection is theoretically D100. The deformation at 100% consolidation. Now we have two values, D0 and D100. With the values D0 and D100, we take a weighted average to find D50, the deformation at 50% consolidation. The weighted average is calculated in the upper left-hand corner of the plot. D50 is equal to 1037.5. Next we find 1037.5 on the y-axis and read off the corresponding time, T50, from the plotted data. This value is the time it takes for 50% consolidation to occur under that unique pressure in which you are applying to the sample. T50 in this case is 10.6 minutes. Now it is time to calculate the coefficient of consolidation. The time factor, big T50, is a constant found in established tables of degree of consolidation versus time factor. For 50% consolidation, the corresponding time factor is a constant 0.197. Always in the case of the consolidation test, the two-way drainage condition is met. This means that a void in the soil has two paths of travel for expulsion, bottom or top. Therefore, the drainage path is half of the clay layer. The deformation corresponding to 50% consolidation was measured to 10 to the minus 4 inches. Therefore, the initial sample height minus the deformation at 50% consolidation divided by 2 is the height of the longest drainage path of the clay layer for a void. Finally, the coefficient of consolidation comes to 3.73 times 10 to the minus 3 square inches per minute. Now we will overview Taylor's method, which utilizes a square root of time axis on the x. Because a parabolic assumption in the Casagrande method was formulated, Taylor's method follows the same train of thought with an assumed straight line portion to find d0. Also, Taylor's method assumes secondary effects below 60% consolidation are negligible. Note that D90 is directly found using Taylor's. D90 being the deformation at 90% consolidation. Based on linearity, we calculate D100 using the equation 10/9 times D90 minus D0 plus D0. Finally, D50 is calculated from the same weighted average as used during Casagrande's method. We will look at a construction as an example. This method is empirical and is used from previous experience. We must remember this when performing its calculations. First, a straight line is drawn tangent to the early portion of the consolidation data. Theoretically, it should be a straight line passing through the early data set and intersecting the y-axis at d0. Since time t equals 0 does exist on a square root of time plot, d0 should be close to the first gathered data point. First, draw a tangent line that passes through the early portion of the dataset, intersecting both the x-axis and y-axis. Record where the line intersects the x and y-axes. The y-intercept came to 880 in our plot. The x-intercept was 8.75 as shown. Taylor's method employs a 15% increase or 15% step along the x-axis to find the next intersection. Therefore, we multiply the intersecting x value by 1.15. We multiply 1.15 by 8.75 to get 10.06 as shown in the upper left-hand corner of the plot. Find this new value on the x-axis, i.e. 10.06. Now draw a straight line from d0 to the new value, i.e. 1.15 times the x-intercept. So a new line is then drawn from 880 on the y directly to 10.06 on the x. Wherever the new line intersects the actual dataset, draw a vertical line down to the x-axis and a horizontal line down to the y-axis. The intersection of the y-axis and this horizontal line is considered to be D90. Our horizontal line crossed the y-axis at 1092, therefore D90 is 1092. With D90 and D0, we now use the first equation to calculate D100. D100 is equal to 10/9 times D90 minus D0 plus D0. By linear interpolation, D100 is calculated to be 1115. We now use the same weighted average equation that we used during Casagrande's method to calculate D50. That is, D50 is equal to D0 plus D100 all divided by 2. D50 is then the average of 880 and 1115, which comes to 998. We now locate D50 on the y-axis and draw a horizontal line intersecting the line to the dataset and find the corresponding square root of time. A horizontal line at D50, which was 998, is depicted here, and a perpendicular line takes off from that intersection, and 3.5 minutes to the 1/2 is read off. Remembering that the x-axis is in units of square root of minutes, we realize that the square root of T50 is 3.5 minutes to the 1/2. With the square root of T50 from the previous plot, we simply square both sides of the equation to obtain T50 in units of minutes. By squaring 3.5 minutes to the 1/2, we see that T50 is equal to 12.25 minutes. With D50 and T50, we then calculate the coefficient of consolidation. Since the test drains in two directions, we divide the compressed sample thickness by 2. Recall that the time factor at a degree of consolidation of 50% is 0.197. After computation, the coefficient of consolidation comes to 3.26 times 10 to the minus 3 square inches per minute. This result aligns with Casagrande's result. This makes sense because the two time deformation plots were constructed from the same pressure increment. Not only are the results on the same order of magnitude, but they are within 13% of one another. This ensures our methodology is correct. The goal in reducing the data for the consolidation test is to develop a void ratio as a function of log pressure plot. The first step is to calculate the height of the solids, which leads us to the initial void ratio. Then, by assuming one-dimensional consolidation throughout the test, we can solve for the void ratio at each load increment, given the height measurement. We will begin by going through the calculation steps. We will first calculate the dry mass of the total specimen. The dry mass of the total specimen is equal to the moist mass of the total specimen after test, divided by 1 plus the water content of the specimen taken after the test in decimal form. After the test, the mass of the ring plus wet soil was weighed to be 285.9 grams. The weight of the ring initially was 145.9 grams. 285.9 minus 145.9 is equal to the wet mass of the soil specimen. The water content after the test came to 0.24, which was 24%. The total dry mass of the specimen was calculated to be 112.9 grams. After converting from grams to pounds, the dry mass is 0.2488 pounds. Next, we calculate the volume of the solids. The volume of solids is equal to the dry mass of the total specimen divided by the specific gravity of the solids times the density of water filling the pore space. So we divide our total dry mass, 0.2488 pounds, by the specific gravity of the solids, which was 2.7, times the density of water, 62.4 pounds per cubic foot. After computation, we obtain the volume of the solids, 0.00148 cubic feet. The equivalent height of the solids is then calculated. The height of the solids is the volume of the solids divided by the specimen area. This is the cross-sectional area of the test specimen. The equivalent height of the solids is the volume of the solids, which was 0.00148 cubic feet divided by the known cross-sectional area of our specimen. The ring's inner diameter is 2 inches, therefore the cross-sectional area of the ring is pi times 1 inch squared. Once the volume of the solids is divided by the cross-sectional area of the specimen, a conversion from square inches to square feet is made. Then after converting from feet to inches, the height of the solids is solved to be 0.812 inches. Since the height of the ring is 1 inch, we know that 81.2% of the specimen is composed of solids, and the remaining percentage is composed of voids, i.e. water and air. The initial void ratio is then calculated based on one-dimensional consolidation theory. The initial void ratio is the initial specimen height minus the height of the solids, all divided by the height of the solids. Since the height of the ring is 1 inch and the height of the solids was calculated to be 0.812 inches, the initial void ratio is computed to be 0.231. Therefore, the initial specimen was composed of 23.1% voids based on one-dimensional consolidation theory. Next, we must calculate the specimen deformation under each load increment. The change in specimen height is calculated to be the deformation reading at various times in the test, which we will take to be our final reading for simplicity, minus the initial deformation reading, or the first reading, minus the machine deflection or apparatus deflection. Note that the machine deflection corresponds to a unique load as predetermined in the load sequence. The end result is delta H, which is the change in height under a unique load. With the specimen deformation, we can calculate the actual specimen height, which is the initial height minus the change in height. Note that delta H is cumulative as we move from low to high pressures. Therefore, as long as we keep increasing the actual stress on the specimen, the total height will keep decreasing. Next, the void ratio is calculated based on one-dimensional height change. The total height minus the height of solids, all divided by the height of the solids. Big H, total height, and E, void ratio, are calculated for each independent load increment. As long as we increase the pressure, big H will decrease, and E will decrease with it. This is our consolidation worksheet. Notice the predetermined load schedule is in the far left-hand column. The change in height is next and is unique for each new pressure. The total height follows, which is directly measured from the change in height. The void ratio is then calculated based on the total height at the end of each load increment. Using the previous equations, the table is easily constructed for a full load schedule. We will now use the void ratio and pressure columns to construct a void ratio log pressure plot. Displayed is the void ratio log pressure plot. Engineers can now predict the void ratio of a given soil at a particular axial stress. The early portion of the data shows a slight decrease in void ratio. Notice how below 1 TSF the data follows a slight slope, whereas above 1 TSF the data follows a sharp or steep slope. This is due to past pressures or the past history of the soil being loaded. The soil has seen pressures at or below 1 TSF previously in its lifetime, whereas it may not have seen pressures above 2 TSF. The last or bottom portion of the curve displays how the soil will rebound after being loaded to 16 tons per square foot. The load is slowly decreased after the peak, and the void ratio increases as the actual stress decreases. Important design parameters will now be derived from this plot. Two parameters, compression index, C sub C, and swell index, C sub R, can be derived from the E log P plot. By drawing a tangent line to the loading portion of the dataset beyond that of the pre-consolidation pressure, we derive the compression index. By drawing a tangent line to the rebound or unloading data, we derive the swell index. The semi-log plot allows us to accurately read off these slopes. C sub C in this case came to 1.03 times 10 to the minus 2, while C sub R came to 2 times 10 to the minus 3. These are important design parameters when estimating settlements of clay layers beneath loads. This concludes the procedures and data reduction sections of the consolidation lab.